Hi, I am Pietro Ferrero, and in this short talk I will discuss some progress in the study of the analytic bootstrap for one-dimensional conformal field theories, using a method based on the study of transcendentality of the correlation functions in perturbation theory. In the second part of the talk, I will also present an application to n=4 super-Young mills. The results that I'm going to discuss are based on a paper published with Kosik Ghosh, Aninda Shingya, and Abdullah Ahmed, and also, for the second part, on some work in progress with Fernando Aldai, Carlo Meneghelli, and Pedro Liendo. To motivate our study of one-dimensional CFTs, let me mention that these theories are in principle very simple. And the reason for this is that at 4 points there is only one cross ratio, and the conformal group is the smallest possible one. However, at least from the point of view of the analytic bootstrap, these theories are also hard to study, because many powerful techniques that apply to higher dimensions do not apply, or do apply but with some caveats, to 1D. And I'm thinking, for instance, about large spin perturbation theory, the inversion formula, or Mellin space. And this is why we decided to propose our method based on transcendentality. To study this method, let's consider a toy model, which is a specific kind of 1D holographic CFTs, where the ADS Lagrangian is extremely simple. It's just that of a free scalar with a 5⁴ type perturbation. The kinetic term fixes from in the CFT side the leading order correlator to be that of a generalized free theory, and the 5⁴ type perturbation fixes the OPE between two fundamental fields. And this also determines the spectrum of the theory, at least as far as we're concerned. This is made of double trace operators, which have the schematic form, which you can see here. What we're going to compute in this theory is 4-point functions of identical scalars, which can be expressed in terms of a function of a single variable, z, which is the 1D cross ratio. The tools that we're going to use are the 1D conformal blocks, which can be expressed in terms of a hypergeometric function, and crossing symmetry. And the results that we're going to find are correlation functions and CFT data, that is, scaling dimensions and OPE coefficients of the double trace operators. The question is then, how can we extract this data in one dimension? And to answer this, let's start from the first perturbative order, that is, tree-level. At tree-level, we can make an ansatz for the correlation functions, which is based on the following observation. Conformal blocks are very simple for integer scaling dimension. Here you can see what happens for delta=1 and 2, but the structure is more general, and it leads us to formulate the following idea. We can make an ansatz which has the same structure of the conformal blocks, plus some terms that are required to implement crossing symmetry. The ansatz is the following, and it is in terms of 3 rational functions and 2 transcendental functions, which in this case are simply logarithms. Now that we fixed the transcendental structure of the correlators, we need to put some constraints on the rational functions. And the constraints that we're going to use are essentially crossing symmetry, a transformation property of the 1D conformal blocks, and the knowledge of the first terms in the S-channel OP, which is the small z expansion of the correlation functions. And this allows to fix completely the rational functions up to some free parameters that are not random, but they are exactly in one-to-one correspondence with tree-level correlators in ADS2. This result is not surprising, but it's encouraging, and this is why we can try and push our method to the next perturbative order, which is one loop. At one loop, things are a bit harder, and in particular we first of all need to enlarge our basis of transcendental functions. Indeed, we will consider harmonic polylogs with degree less than 4, or transcendentality less than 4. The second important point at one loop is that we have some new constraints that come from what we could call the ADS unitarity method, because it's quite reminiscent of the unitarity method for scattering amplitudes. To understand what this is, let's consider the small z expansion of the correlator, and one can see from general arguments that there is a term which contains log squared of z, and then there are some pieces that I'm hiding here which only contains logs or are analytic for small z. This log squared term is given in terms of a sum, which contains only CFT data that are known from the previous orders. And this allows to compute this sum and fix completely this term in the correlation functions. We can also express this idea of unitarity method pictorially, and here we can see how we can reconstruct sort of the cut of a one-loop diagram in terms of products of three-level diagrams. The generic result that we find at one loop has this form that you can see. Of course, it's not particularly nice because it's a one-loop result, but it's given in terms of our basis of transcendental functions and in terms of some polynomials which one can fix for every integer delta phi. Given the success of this method to one loop, we can consider an application. And this application is a 1/2 BPS Wilson line in n equals 4 super young meals. This is more properly called a Wilson-Maldacena line, and through the correlation functions along the line, it defines a super conformal field theory, a defect conformal field theory, in planar n equals 4 super young meals. The correlators in the defect theory are computed inserting a supersymmetric Wilson line operator as well as the operators of n equals 4 along the same line. And this theory, as I said, is superconformal, and the superconformal algebra it enjoys is OSP 4*/4, which contains three bosonic pieces, SO1,2, corresponding to the 1D conformal group, SO3, corresponding to rotations around the line, that's why it's called the transverse spin, and finally, it has an R symmetry SP4, which is isomorphic to SO5. The holographic dual to this configuration can be studied in the n equals 4 ADS5 x S5 ADS-CFT correspondence, and in particular, it is known that in Wilson loops in planar n equals 4 super young meals at strong coupling are dual to open string minimal surfaces in ADS5 x S5. For the specific case of the 1/2 BPS Wilson loop, the minimal surface is ADS2, and this allows to study this configuration from the point of view of the ADS2 CFT1 correspondence. Finally, a particularly interesting operator in this conformal field theory is the superconformal primary D1, which is a 1/2 BPS operator and has thinking labels 0, 1 under SP4, or is in the fundamental of SO5. This is dual to the ADS field YA, with A an index ranging from 1 to 5, which is again in the fundamental of SO5, and this is important because the ADS Lagrangian for such field is known as a perturbative expansion around the free theory, where the perturbative parameter is 1 over root lambda, lambda being the 't Hooft coupling. There's not only D1, but there's a full family of 1/2 BPS operators on this line, which we'll call DK. They have scaling dimension k, 0 transverse spin, and linking labels 0k under SP4. The OPE between two such short operators contains other short operators as well as some longs. But if we focus on the short sector, we can see that localization fixes the OPE coefficients in this sector in principle to all orders in 1 over root lambda. And this is going to provide an important input to the bootstrap problem. We can study then correlation functions between such operators, and in particular we study correlators of pairwise equal operators, and in these correlators we observe some miracles of supersymmetry. The first miracle is related to the fact that these correlation functions have lower transcendentality than a generic case. In particular, the transcendentality only scales with L is the number of loops, whereas in general it scales with 2L. So it's lower than it might be in general. The other miracle is that the degeneracy between operators is not lifted at tree level, meaning that operators that have the same scaling dimension in the free theory are still degenerate at the first perturbative order. This is very important for us, and it allows to fix exactly the correlators up to 3 loops in perturbation theory, with a little caveat, which is that to fix the 3 loops result exactly, one needs to solve this degeneracy, this mixing problem, at 1 loop. To give you an example of our results, I'm going to show you here the correlator D1, 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 D1 at 1 loop, which is entirely fixed in terms of this rather simple function, which as you can see only contains log squared, but not higher polylogs. And therefore, we can say that the result is much simpler than the generic case. In case you don't believe me, I'm going to show you again what the generic case looks like, and therefore we can really see that n equals 4 is much simpler. This project is not quite concluded, there is some work in progress. In particular, we're trying to solve this degeneracy, this mixing problem at one loop, and in principle, this will allow us to find the 3 loops correlators exactly. To conclude, let me tell you that there are some generalizations of this method that we already studied. In particular, we applied it to fermions with half-integer scaling dimension, to models with global symmetries, and also to non-protected operators, so with operators that have a non-integer dimension seen as a perturbative expansion around integer dimension. Other possible applications of this method are other Wilson line, so n equals to 2 theories in line defects, or line defects in a BJM and other applications, but also a very interesting model in one dimension, which is the SYK model. And finally, it's quite possible that the study of higher point functions is also simplified in one dimension, since there are always fewer cross ratios than in higher dimensions. And to conclude, let me thank you for your attention.